Hi, and welcome to the second video in our series. This one's going to be about hashing as a data structure or hash tables as a data structure. Let me share my screen and we'll get started. I'm going to give you an overview of hashing. A lot of detail about hashing is provided in the Zeit book, and there are a lot of good exercises and quizzes there that will really help you on the details. I'm going to try to give you the big picture. In other words, explain how hashing fits with other data structures we've learned so far, like arrays and lists, and why it's such a useful data structure in general. I would say that if you have hashing, you have some form of implementing hashing, you hardly need any other sort of data structure. That's a fairly bold claim. But I know that if you really had to, you could simulate most other data structures using hashes and maybe lists alone. Now, the result might be clumsy, but hashes are actually that flexible. The ability, there are other useful structures, that are more convenient in some applications. We'll study them, trees and B trees. They make life much easier, but hashes are very, very general and they're very fast, even when they're very big. So they're widely applicable. The ability to store and retrieve and delete key values by key, to have these key value pairs is so useful that hashes are implemented in just about every programming language. Python calls them dictionaries, and we'll study those directly since we're using Python as the main language for our data structures course. Java calls them hash maps. So if you've studied Java up until this point in your software development career, you'll find hashes are there in terms of hash maps and hash sets. Lua, which you may not have studied, but which is a useful little scripting language that actually pops up every now and then in games as a game extension language. Lua calls hashes tables, and it's built pretty much entirely on tables. Awk, an ancient text processing language that you probably have never heard of unless you've taken the Linux shell scripting class. It has hashes and calls them associative arrays. Associative arrays is kind of an old-timey term for the same thing. It allows you to associate a key and a value. And of course, Perl, another ancient language, is pretty much built on hashes, uses hashes almost. Perl was actually implemented using hashes. Not only does it offer hashes as a feature for the user, it is actually implemented in hashes. So let's think back a minute to what we talked about with lists and arrays in the earlier videos. Those structures work by what I call address calculation. In other words, knowing the starting address of the array, which would be ampersand list 0 in C, and an integral index, meaning an integer index like a byte or a char or an int or a short or long, the exact memory location for the element you want is worked out by just multiplying and adding. You take the starting address of the array, you add to it index times the size of the array element, and you have a machine address that will take you directly, order in sub 1, to that element. So they're very efficient and very fast. Now, we talked about fancy arrays versus plain vanilla arrays. So the element you're taken to by this address calculation might be already directly the value that you want, or it might be a reference or a pointer to a value stored elsewhere, which is probably what you need for a couple of reasons. One is if your array elements are objects, you might want to just have references to them in the array to keep the size down. And they also, these fancy arrays that use an indirect reference from the element to the value are also, they facilitate growing and shrinking the array. And that's very handy for a lot of array implementations, including, for instance, queues and decks and stacks, which are mentioned in the initial chapter. Those all work a lot better if you have a dynamic or adjustable arrays. In a direct way then, an array index, the number you put in the parentheses or the square brackets, you can think of that as a key, and it's used to fetch the value, and the value is whatever you put in the element. So in a limited sense, in a very basic but high performance sense, arrays and lists are key value pairs. You're going to see that just gets extended in hashes and generalized in a way that's very, very useful. So hashing is really a generalization of arrays and lists. A hash is key value pairs, but the keys can be any object, usually strings, and the values can be anything you want. So hashing keeps the idea of fetching or inserting a value based on a key, and that's order in one. So in other words, it doesn't depend on the number of elements of the array. And hashing generalizes this, though, by removing some constraints. Now, these constraints are what make basic arrays so fast. But by constraining the indices, which are like keys, to be integers, you ensure that you can access them really quickly because compiler is really good at generating code for calculating machine addresses. Hashing, you remove that constraint. You say your keys can not only be ints, they can be almost any kind of value. They can be object values, and the most common type of object to use as a key in a hash is a string. That's really convenient for looking up one value from a string value or one string from another. So with hashing, you can store key value pairs, sort of like you did with arrays, but the key is usually a string like ABC123, and the value can be another string, a number, or any sort of object that you want. Retrieving things from a hash is still order 01 because the time required in theory, in absolute terms, to fetch the required element from the key does not depend on the number of items in the hash table. So that means that hashes stay very fast even when they get very big. And that's one of their big attractions. Inserting into a hash table, as you know, if you look through the chapter 4, is somewhat more complex because you might have to make adjustments or search multiple elements in the array in order to find a place to put the new value. But retrieving things from a hash is just a matter of giving a key, doing a calculation, and going directly to the bucket that contains that key. So it's still pretty fast. So instead of using address calculation, what I'm calling address calculation, hashing uses what I'm calling address compression instead. So here's the little terminology you need to know. Keys determine which bucket in a hash will hold the matching value. If you want to think about arrays, I suppose the elements themselves, the locations of the elements were buckets, but hashing actually uses the term bucket to denote the place where you end up putting the value and any other information you need for retrieval. So hashing maps a key into a bucket. You need this compression of keys because if you look at like string valued keys, well, you might have some very long string valued keys. Consider the name of this course, kind of all crunched together into one string. If you treated that as a number and you just tried to index directly into it, it would be a huge number. And because I'm not sure how many bytes it is, but it's a big number. And there'd be a huge range of possible values from the letter A to the letter Z. Not very practical in memory. That's what the Zai book refers to as direct hashing in section 4.8. It took me a while to figure that out because it's so impractical. I couldn't figure out what they were talking about. It might work in theory to just literally take the string, treat it as a number without doing any compression to it, and go looking for the appropriate bucket, but you're going to need a very, very large hash table and a lot of buckets. So it doesn't really work. Hashing is just a way of compressing that range of possible keys, or hash functions are a way of compressing that range of keys so they fit in a much smaller hash table while still retaining fast lookup. So let's look at how keys get converted to compressed bucket addresses. For the moment, let's stick to string valued keys because those are the most common, but do know that a key could be any data type. A potentially long string key, to summarize that, you add the individual characters up into a total. So you do a little bit of arithmetic on the letters that comprise the key string. So if you get A, B, C, D, you add up the ASCII value of A plus the ASCII value of B plus C plus D, and you get a single number. You get the same number, it's order independent because you're summing, if you add up B, A, D, C. They add up to the same sum. Now, that's reduced that key space already from requiring a number that's 4 bytes in size to a number that's much smaller number of buckets. Uh, the in order to keep it in range, even though you compressed it, it still could be a large range of numbers. The sum that you get from adding up all the elements in the key is remaindered using the modulo operator. Now, what does that mean? That means that you mod the number using, and you get the remainder, you basically divide it by the size of the hash table and take the remainder. What that does is to ensure that the summed key cannot get outside the hash table, because it's basically scaled down to fit, and that operation is actually also very quick. The summarized key is remaindered by the number of buckets in the hash table. So if your hash table is 100, you remainder the value you get when you add up A, B, C, D by 100, and whatever amount is left over, which is guaranteed to be less than 100 arithmetically, use that to get the bucket number. So that guarantees that the key you produce by this compression will fit in your hash table. It won't overflow. But that brings up a problem we're going to discuss in just a minute. So that, it sounds perfect. That's a good solution. You can see that it would be fast because adding up characters and doing a modulus operation on them is extremely fast. Integer arithmetic that computers are good at. Where's the problem? Collisions are the problem. Even in the example we looked at, ABCD versus BCDA, those two keys will end up wanting to live in the same bucket. And that's actually not going to work because the value associated with one of them might be a lot different from the value associated with the other. You need to be able to retrieve them separately and get their associated value, even though in the naive original implementation, they end up in the same bucket. That's called a collision, and that's a lot of what hashing is actually doing and spending its time doing, is sorting out, either preventing collisions or remediating the effect of collisions. So there's two things you can do. You can try to avoid collisions. You can try to resolve them when they occur. You actually have to do both. Choosing the right hash size, like make it a prime number, choosing a good hashing function. There are many to choose from that are described in your textbook. Those things, making it the hash table big to start with, those things all reduce the probability of collisions, but they don't bring it to zero. So you still have to be able to resolve a collision when, after all your best planning, you still end up with two keys that want to use the same bucket. So a lot of what they're showing you in chapter 4 is devoted to this kind of stuff. There really are two approaches that work, two families of approaches that work for collision mitigation. One of those is the they'll talk about, the book talks about the linear programming, linear probing, not linear programming, linear probing, quadratic probing, and so on. Those are simple, relatively, algorithms for finding the next empty bucket after a collision has occurred and storing enough information so that you can, on search, find the correct bucket for this key value, given that there's other keys that map to the same value. So that's, and the project for this section, this module, has you implementing some of that stuff, has you implementing linear programming or, linear probing or some other algorithm for collision resolution. Another way to resolve collisions, which is also very popular, combines hashing and lists. So when two keys hash to the same bucket, you just add an element in a linked list, an array basically, in Python, and you put each of the ones that collided in their own element, or list element, with enough information so you can retrieve them. So the search algorithm then becomes find the bucket and go down the list of collisions for that bucket until you find the one that has the key you really wanted. In summary, if you look at the approach we're striving for in this class, I want to take a minute to explain this. Probably should explain this in the first video. Here we are in the second, but what the heck. We're learning to apply and use efficient and well-debugged data structures, the ones that are provided in Python and other programming languages. Those tools exist. They're highly optimized. They're highly debugged. You will probably never write your own hashing function because Python dictionaries have got that down and they've been refined by experts. So they're really good. And you or I are unlikely to ever be able to do better. But in learning how these are implemented, as well as learning how they're used, you can understand a lot more about why you might choose this data structure. So it's necessary to go into some implementation detail, which the projects do, in order to fully understand what distinguishes one of these data structures from another and how they're alike or different. And that's what the project in this module attempts to have you do. It's also important to learn the concepts, to talk intelligently about these structures and their relationships, which I've tried to talk a lot about, how arrays and lists are the same thing, and essentially hashes are generalizations of arrays by removal of constraints, those kind of things. Kind of the meta language approach. And to talk about their theoretical performance. It's important to know that hashes are order 1 for searches, because that is a very important parameter that may help their performance as they grow larger. It's also important from a practical sense to be able to talk about this in interviews, because that's really part of Dr. Macon's original impetus for this class, was to set up a data structures class that enabled students to deal with the fact they were being asked in interviews about data structures, and none of our existing courses really treated the data structures. We treated algorithms. We didn't really treat data structures as a separate topic into which we went in any depth. This course does that. So a typical situation might be, and I've actually read about this one on the internet, people talking about their interviews. Interviewer says, well, what's a dictionary in Python? And you say, well, a dictionary it's a hash table. It lets you put in key value pairs. And then the follow-up, so far so good. Then the follow-up question, well, how does that work? Okay, now you need to go below the surface, below the just how to use a dictionary, and be able to talk intelligently about the implementation. You need to say, well, there are these things called hashing functions, and they compress the keys so that they fit in the hash table. And the hash table has the logic so that if 2 keys end up in the same bucket, it gets resolved. And hash tables are very fast because the time required to do this operation doesn't depend on how big the hash is. That would be a great answer, and you probably would not need to go below that. So you need to be prepared. This class is also to help you prepare for, a more than superficial level understanding of data structures. So I'll leave it at that, and we can go into some other information about data structures. It's important to do the project because I went through the Zybook and I went through some of the exercises and the quizzes, and wow, this is straightforward. This is easy. I got this stuff. And I thought I understood it really well. Then when I went to code it in Python, I realized, well, wait a minute. How does this linear probing thing work? I've got the same key in 2 buckets. How do I know which one's which? Turns out you have to store the key along with the value in the bucket. That was not apparent to me until I tried to code it and said, whoa, this is not going to, my initial implementation was not going to work. Now I went back and the Zybook explains all that, but I had missed that. So by doing the projects, I think your understanding of the concepts will actually get more clear, and you'll feel more confident, not only using the data structures to do your own programs and solve problems with them, but using the data structures in order to talk about them intelligently to other people. That's all I have for now. Thanks a lot, and I will see you in the next video. As always, message me in Canvas with questions or issues. Thanks a lot.